Okay, welcome to lesson 7.6, reaction mechanisms. Reaction mechanism is a fancy term for what pathway does a reactant undergo. And you guys are used to noticing in a chemical reaction, you tend to see reactants and products. However, reactions are not that simple. They actually go through a specific pathway. And not a specific pathway, but a certain pathway. And that's what we're going to look at in a bit. Before I talk about these reaction pathways or the reaction mechanism, you have to know what elementary steps are. So elementary steps are just a sequence of steps in which you're making certain products. So for example, right here it says elementary steps or elementary reactions. Reactions turns to product in a single step. So a reaction's molecularity is defined by the number of particles that participate as reactants in an elementary step. So for example, here we have CH3CN, and then it makes another product, and this product has the C and the N switched off. So this is an isomer, and it's an elementary step because it's undergoing one specific reaction. However, this is called unimolecular because we only have one reactant. So one reactant produces one product. It could be two products and it still be unimolecular. What we're looking at is the reactant. So one thing is going to change. However, down here we see two reactants, and we call this bimolecular because two substances are going to actually collide with one another, and it's going to generate some sort of reaction. And termolecular is very rare. We don't talk about them because it's extremely rare. We normally don't see three reactants banging into each other and resulting in a chemical reaction. It's just very rare that three substances are going to collide in a very specific fashion to produce very specific products. So we don't really talk about termolecular reactions or termolecular elementary steps. So this doesn't make much sense right now, but it will in a bit. For multi-step mechanisms, there is a sequence of elementary steps in order to go from reactant to product. So for example, you guys are used to seeing a general reaction like this. So NO2 reacts with CO to make NO and CO2. You guys have been used to this for a very long time, but in reality, you're not going to see NO2 colliding with CO to make these two substances. This is called an overall reaction. This is a reaction that can actually be split up into separate reactions or separate elementary steps. So for example, at the very beginning, look at this part right here. Elementary step 1. We have NO2, and it's reacting with another NO2 to make NO and NO3. So this is one step, okay? The whole point of this first step is to make something called an intermediate. An intermediate is basically some substance that is produced, and then it's immediately consumed to start a second reaction. So for example, do you guys see NO3 in this overall reaction? You don't, because NO3 is behaving as an intermediate. So this NO3 that's produced is now used up in a second reaction with CO to produce NO2 and CO2. So once you cancel all the substances that are found on the left and on the right, for example, NO2 is here, and then it's also on the right here. So you cancel it. You guys learned this already. Very similar to Hess's law. back when we did the thermal chem unit. And NO3, the intermediate in this case, cancels as well. And then we're left with our overall reaction. So once we cancel, we're left with NO2, CO, NO, and CO2. So, like I said already, this overall reaction that we're used to, it's not like you're making it's not like NO2 is colliding with CO to make these products. It's actually, this whole reaction is actually a product of elementary steps that occur. And we typically don't write these because, this is really what is being, consumed and what is being produced. It's just that certain intermediates help, to make certain products. So, one of the key things about this is that you guys have to know which substance here is the intermediate. The intermediate is always a substance that's produced, but then it's immediately used up in the second reaction. So for example, NO is produced, right? But it's not consumed here. So it's not an intermediate. NO3 is produced and it is consumed and it's not part of the overall reaction. So that's the intermediate. All multi-step mechanisms have intermediates. And it's not going to be a reactant nor a product in the overall reaction. Just keep that in mind. It's never going to be one of these four. It's always something that's missing, because it serves as an intermediate. So here's an example. I'm going to do this one actually, and then you guys are going to try that one. So for this one, it says, given the conversion of ozone into O2 by a two-step mechanism. So here we have ozone, it's making O2 and O. Here we have ozone again, but it's reacting with O, and it's making 2O2. The questions, 3 questions, say, describe the molecularity of each elementary step in this mechanism. So what it's saying is it bimolecular, unimolecular, termolecular? So by looking at the first one, we could tell that, let me rewrite the equation, O3, I'm just going to ignore the states of matter. Because there's one reactant, it's going to be unimolecular. And then the second reaction, O3 plus O makes 2O2. Because there are 2 reactants here, this is going to be bimolecular. The second part of this question says to write the overall reaction equation. Okay, and then the second part says write the overall reaction. So because O3 is found on both at the same side, it's going to be 1 plus 1, so it's 2. I'm going to put a line here. 2O3. This oxygen on the left cancels with the one on the right. And then you have 2 O2s here and 1 O2 there, and they're in the same side. So you're going to put 3 O2 like that. Okay, so this is the overall reaction. It says to identify the intermediate. So what is produced and consumed? So O2 is produced, but it's not consumed here. O is produced here, and it is consumed here. So oxygen on its own. So oxygen, OG would be the intermediate. Okay, so again, intermediates are produced and consumed. Again, it's not as simple as just this is going to form this. It actually undergoes 2 reactions in order to get to this overall reaction. These are called elementary steps, and this whole thing, all 3 of these steps or equations is referred to as a mechanism. So this is a chemical mechanism, or some sort of pathway that occurs. So you guys try this one, and then once you're done, press play. Okay, so now that you tried, I want to go over it. So the overall equation is given to us already, and you're given 2 elementary steps, and it says that, is this mechanism consistent with the overall reaction? So let me do this. So we're gonna basically cancel things out and see if it matches with this. So that's basically what A says. Is it consistent? Does it actually cancel out to form this? So you have to read this carefully. If you look here, MoCO5 is on the right and it's on the left, so it cancels. None of the other substances are gonna cancel here, so it's gonna be MoCO6, which is there, and then PCH33, which is on the left side of this arrow, and it's supposed to be on the left side here, so that's good. And then on the right side of the arrows, you see CO, so CO is there, and MoCO5 PCH33 is right there. So yeah, it is consistent. So A is consistent. Part B says, what is a molecularity? So here, there's only one reactant, so this is unimolecular. Here, there's 2, so this is bimolecular. What is intermediate? So this guy is produced, and then it's immediately consumed. So part C would be MoCO5. So that would be the answer to that problem. Let's see here. So the next problem, the next slide, with everything that we just went over, you guys could already do half of the homework. So if you guys want to start the homework that part of the homework, you guys can, and then come back to the podcast and finish the rest. That's totally fine. Now I'm gonna go over the last part of the podcast. So we learned in the past that rate laws cannot be determined by the coefficients in a balanced equation. And now you guys know why, because rates are, they're not going to happen in a very specific way, because they have multiple steps that they undergo in order to achieve those products. There's a bunch of elementary steps that could occur. There's a reaction mechanism. So we can't use the reactants really in an overall reaction to find elementary steps. However, for elementary steps, not the overall reaction, but for elementary steps, you could use the coefficients. So you can. So for example here, A is the reactant. You could assume A is going to have a first power because there's only one of them. 2 A's means 2 power. A and B means A times B, and each being to the first power. A to the 3, because there's 3 A's. So we could do that for elementary steps. So it says here, these rate laws are for elementary steps, not necessarily the overall reaction. So just keep that in mind. Here, if you guys want to understand what a rate determining step means, what does it really mean, you guys could read this car analogy in your textbook. If you don't want to, like, you don't really want to know the meaning of it, you don't want to make sense out of this, it's totally fine. But, you know, you would have more value in understanding the analogy in correspondence to what a rate determining step really means. So let me explain right now what a rate determining step is. So it says here, most reactions have multiple elementary steps. However, they don't all occur at the same rate. There's always one that is very, very slow. And that is called the rate determining step. And again, if you read the analogy in the textbook, you'll know why the slow one is the rate determining step. So to come up with another analogy, this is another one that I came up with. Let's say you're trying to make vegetables. So at ESAT we have a garden. At some students try to make vegetables out of this garden. The hardest part of actually producing vegetables or food is the growing of the food itself. So in order for it to grow, that is like the most difficult part, the growth, and everything else is easy. It's easy to put water, it's easy to put nutrients, it's easy to put nitrogen or fertilizer. It's easy to tear out the vegetables. However, the difficult part is for the food to grow. So the growing of the food is the slowest, and two, it's the rate determining step, because the growing is what determines whether you're going to produce fruit or not. So in a rate law, we must have the rate determining step within the rate law. So the rate law, the correct rate law is always going to be based on the rate determining step. You have to consider two things. Always have these two things in mind. One, if you're given a bunch of elementary steps, the one that's slowest, the one that has the smallest k value, or it tells you that it's the slowest, that is going to be the rate determining step. But you also have to consider that you cannot have intermediates in the rate law. You can't have intermediates, and it has to be part of the reactants in the overall reaction. So it has to, let me repeat that one more time. It has to have the reactants found in the overall reaction, and it is based on the rate determining step, which I'll introduce in a bit. So here is an example. So in this example, it says that N2O decomposes through a two-step mechanism. So N2O is gonna form N2 plus O. It already says that it's slow. So that means this first one has to be the rate determining step. Then we have N2O again, and it's gonna react with O, the O that's produced here. So that shows us that O is gonna be the intermediate, and it's going to produce N2 and O2 in a very quick fashion. So it says write the equation for the overall reaction. So I'm just gonna rewrite the equation here. N2O makes N2 plus O. N2O plus O makes N2 plus O2. So N2O is here and N2O is here. They're both on the left, so you add them up. You don't cancel, you add them up. O is on the left and the right. O is going to be our intermediate. I know the question doesn't ask for it, but I'm just going to tell you that that's what it is. And N2 is on both sides, so you put, it's on both on the right side. So you add them up and you have O2. So this is the overall equation. It says to write the rate law. So the rate law, we don't use this. Okay, we don't use this. What we look at is the rate determining step. So according to the rate determining step, we only have N2O. So rate is equal to K times N2O, and there's only one. So it's going to be to the first power, okay? I know there's two here, but remember, you could only use the coefficients if it's an elementary step, not the overall equation. So we can't use this 2. We can't put this as squared. You leave it as to the 1 power because it's based on the rate determining step. So this would be your second answer, and this would be your first answer for this particular problem. Yeah, so now you guys could try the next one. So for this one, it says that you have this overall reaction and you have a proposed mechanism. And what it's basically saying is this the correct rate law? So is this the correct one? So you tell me if that's right or if it's wrong, or what can you tell me about this information that's given. So go ahead and give it a try, and then let me go over it. Okay, so now that you tried it, let me find another pen. So you guys canceled, right? And found overall reaction. So you guys noticed how NO3 canceled on both sides here, and you have O3 which is here, and then you have 2 NOs, which is there, 2 NO2s, which is there, and then you have this O2 there and this N2O there. So this is the correct overall equation. The rate law is based on the rate determining step. It's not here, it doesn't tell us which is the rate determining step. However, we're probably gonna assume that this right here is the rate determining step, the first one, because if you find the rate law for this one, for the rate determining step, it's gonna be the same as this one right here. So what can you infer about the rates of the 2 steps of this mechanism? I can infer that this is most likely gonna be the rate determining step because it has these guys included in the rate law, and not these guys. So that's what I could infer. So hopefully you guys got that. Now, this is just a reminder that the correct rate law must have reactants, the reactants in the overall reaction, and not intermediates. So we're gonna see some examples where that is not the case. So again, this doesn't make much sense right now, but it will in a bit once I go over an example or two. So I'm gonna give you 2 examples. You guys will try the last one, the third one, and then you guys should be set with your homework. So here's an example, and here in black we have the overall reaction. It has the following elementary steps. So ES means elementary step 1. Here we have an equilibria, Cl2 to Cl, and it's fast. Second elementary step, we have these guys, and it's slow, so that implies that it's the rate determining step. ES3 has 2 other substances, and it makes this substance, and that's fast. State the rate law. So we learned already that I'm gonna cover this up. State the rate law. So what is a rate law? We learned that the rate law is based off the rate determining step. So it's gonna be equal to K. So let me rewrite that. That was kind of messy. Come on. No. Okay. So rate is equal to K, and rate determining steps this guy. So we use the reactants from the second elementary step, and then Cl. And then we normally stop there, right? But we have a problem. This CHCl3 is part of this reaction. What I'm trying to say is that this CHCl3 is part of the overall reaction, and it is part of the rate determining step. However, this Cl is part of the rate determining step, but it's not part of this overall reaction. So if you go back to this slide, it's based on the rate determining step, but it has to have all the reactants from the overall reaction. So it's violating the second step right here, the second requirement. So what we do when this happens is we have to use a little bit of substitution. So we have to get rid of the Cl because it's not part of this. We want to substitute this so that we get Cl2 somehow. And what you could do is you could use an equilibrium. So out of all the 3 steps, I see that the only equilibrium that I'm given is this first elementary step. So because it's equilibrium, it moves in both directions. So for example, Cl is going to have a rate law of K. We're going to call this K1 to the Cl2. But then it's equal to the rate of the reverse. So we're going to call the reverse K2. And we're going to put Cl right there to the second power. We could put a second power because this is an elementary step. So that's the rate law for this. We want to get rid of Cl. This is Cl2. This is Cl. So we want to get this by itself. So what we do is we're going to divide by K2, and then we're going to square root this. So I'm going to square root it as half, like this, okay? That will get rid of this squared. I'm going to half this, raise it to the half power. So Cl is going to equal K1 over K2 times Cl2. So I'm just going to leave it like this. This is isolated. This is equal to all of this. So what you could do now is, because this is Cl, I could now plug all of this in here because I want to get rid of Cl because it's not part of this overall reaction. So when I do that, I'm gonna need more space here. So when I plug this in there, I'm gonna get rate is equal to K times K1 over K2. All of these K's are gonna form a fourth K value. It's gonna form some random K value. So we just squash them all together. Let's just call it just K. Doesn't matter. Just call it K. And again, we're keeping CHCl3 because that is part of the overall reaction. It is part of the rate determining step. We wanted to substitute in for Cl. We wanted to get rid of it. We wanted to do that using the equilibrium. And so now I'm going to have Cl2 there instead. Cl2 to the half power. So the half power does not disappear. And so this is going to be your new rate law. And on the AP exam, you're probably going to see half there. You're going to be like, what is that? That's probably not the answer. But it actually is, because you had to use a little bit of substitution. So now CHCl3 is part of this overall reactant, and Cl2 is also part of the overall reactant. And our original rate law was based on the rate determining step. I know that was very difficult to understand, so I'm going to go over another example. So here is the second example. A little more simple. So hopefully it'll make sense to you. If you feel like you got it, then you could try it on your own, but I don't expect you to get it yet. So let's do another one. So here is the overall reaction. We have 2 elementary steps instead of 3. It says that this is the slow one. Again, if they give us numbers, use the one that has the smallest K value if they happen to give you K values. So I'm gonna base the rate law on the rate determining step. Rate is equal to K times the rate determining step reactant, NOBR2, times NO. And you normally stop there, but you have to double check that no, it's not, that all of these guys are part of the overall reaction. So NO is good, but BR2 is not here. So that means we have to get rid of this. We have to substitute this somehow. And you learn from the last example that we could use the equilibrium of something. We set them equal to each other. We basically set the rates equal to each other. So you find the rate law of this side. So I'm gonna say it's K, K1, NO, BR. So this is the rate of the forward. And we're gonna say it's equal to the rate K2 of the reverse. And again, I don't want NOBR2, so I'm gonna isolate that. I'm gonna divide by K2. And now NOBR2 is equal to all of this. And now I could basically substitute all of this in here. I'm gonna move this up a little bit. And when you substitute all of that in, you're gonna get rate is equal to, oops, is my pen doing that? Rate is equal to K1, K times K1 over K2. Again, just squash them all together. That's K. And we're gonna put NO and BR2. So NO, BR2 is being substituted in there. And we also have this NO on the side here. So, in other words, the rate is going to equal K times NO squared, because there's 2 of them, BR2, and that's going to be our rate law. And this is the correct rate law because NO is part of this overall reaction, and BR2 is on the overall reaction, and the original rate law was based off the rate determining step, which again, the rate determining step means that without it, a reaction is not going to occur. The rate determining step is the most important part if we want to make any product. So that would be our correct rate law. Let me see, is that the same? NOBR? So yeah, wait, is this another example? Okay, so here's another example, and this one gives us another set of elementary steps. So this one, is the same overall equation, but the elementary steps are a little bit different, but I believe we could still get an answer for this one. So we'll see what the correct rate law for this one is. So you guys could try that one now. See if you get it right. Once you try, go ahead and check your answer. Okay, so you guys wrote the rate is equal to K times H2O2 times Br2. So this is based off the rate determining step, which is the low step. However, you notice that N2O2 is not part of the overall reaction, so you have to substitute that in, and you have to use the equilibrium. So what you do is you set these equal to each other, the rates equal to each other. So you're gonna put K1 for this one, times NO squared, let's say, because there's 2 of them, is equal to K2, the reverse, which is N2O2. And again, we want to get rid of N2O2, so we want to get this by itself. So we divide by K2. And all of this, we plug in there. Because this is N2O2, we substitute that in. And when we do that, we get KNO squared. Remember, all three K's form another K value. Just call it K. And BR2, which is left over here. So this is the new rate law, which does include NO, and it does include BR2, and it is based off the rate determining step. So that would be the correct answer. For these last few slides, they're just concepts that you have to know. I'm not sure if they're going to be on the AP exam, but just so you guys know, enzymes, catalysts are substances that bind to molecules. So for example here, you guys notice how NO and BR2, they react. Sometimes they don't react very well. So what happens is that a catalyst comes in and binds them. It binds them, it helps them break bonds, and helps them form new bonds in order for a chemical reaction to actually occur. So like it says here, catalysts bind to reactant molecules onto active sites. So they're just specific regions where the catalyst could actually bind to them. The reactants are broken or weakened, and it allows the activation energy to drop, and then that triggers a reaction. So a product can actually form. The enzyme then detaches itself. It's not part of the reaction. It's not consumed. It's just there. It just helps it. Specific types of catalysts include enzymes. So enzymes are biological proteins, and they usually have very, very specific functions. For example, lactase, which is an enzyme found in your tongue, helps you decompose a protein called lactose. Not a protein, a sugar called lactose. And it helps it decompose. So enzymes tend to end in ase, and they have very specific functions, and they help trigger reactions. They help break down reactions and form new ones. Substances that react to these active sites are called substrates. So substrates are just basically, it's just your reactants. So your reactants are your substrates, and then your enzyme comes in and it binds to the substrate, and it forms this complex. So here's your enzyme, and here's your substrate, which is your reactant. The enzyme comes in, and it's shaped in a specific way, so that it triggers some form of formation. So here it is. It forms a lock key kind of model where, you know, in order for a key to work, it has to fit in a specific way. The same thing here, in order for an enzyme to work, it needs to fit in a very specific way. And then you form your product. So here we had one piece, now we have two pieces. So thanks to the enzyme, it helped to slice this reactant into two. This complex is called the enzyme substrate complex. Again, that's how enzymes work. And just like enzymes help form new stuff, there are something called enzyme inhibitors, and it's actually very important in medicine. So if you want something to stop working in your body, you need to have enzyme inhibitors, which basically bind to the active sites and prevents enzymes from triggering new reactions. So for example, poisons, lead, mercury, these are enzyme inhibitors that tend to block the formation of products. So that's why these substances tend to be dangerous to our bodies, and because they block very important cellular activity that occurs in the body. And that's basically the end of this lecture. So go ahead and start your problem set, and you should be set.